exploration. Rocket physics. To introduce physics today into our segment regarding the solar system and spatial exploration, we can start with the device we need to get to outer space and how it works, our friend the rocket. In basic terms, a rocket creates a push by removing mass to take advantage of Sir Isaac Newton's third law. To every action, there is always an equal and opposite reaction. In a rocket, combustion increases the temperature of gas that is in the engine, and it expands and rushes out the nozzle of the rocket, and that's how the rocket is pushed in the direction it needs to go. Solid propellant rockets have been used for centuries, operating on the same basic principle but with different reaction mass and combustion chemistry. Today, they are used as strap-on boosters for liquid fuel-launched vehicles, for orbit injection stages, and for many standalone rockets. Modern rockets have a core of propellant made of mixture of fuel and oxidizer in solid form held together by a binder. Once ignited, a solid rocket cannot be shut off. Liquid propellants have the advantage of fairly high density, so the volume and mass of the propellant tanks can be relatively low, resulting in a high mass ratio. Liquid rockets, once started, can be shut off. Some kinds can later be restarted in flight. A useful parameter that indicates a particular rocket engine's efficiency is its specific impulse, ISP, which is a ratio of the thrust produced to the weight flow of the propellants. It represents the impulse change in linear momentum per unit of propellant. The higher the specific impulse, the less propellant is needed to gain a given amount of momentum. ISP is a useful value to compare engines. A propulsion method with a higher specific impulse is more propellant efficient. Space missions. The first scientific discovery made with instruments orbiting space was the existence of the Van Allen radiation belts, discovered by Explorer 1 in 1958. The Van Allen radiation belts are donut-shaped zones of highly energetic charged particles trapped at high altitudes in the magnetic field of Earth. You can see this to the right in blue. Several space missions have investigated Earth's magnetosphere, which is the surrounding region of space in which the planet's magnetic field exerts a controlling effect. Early space science investigations showed, for example, that luminous atmospheric displays known as auroras are the result of the magnetosphere interacting with solar winds, and the scientists came to understand that the magnetosphere is an extremely complex phenomenon. Space physics was later extended to the understanding the characteristics of the Sun. Exploring space between the Sun and Earth and other planets is called the interplanetary medium, which is to the right, which is thinly scattered matter that exists between the planets and other bodies of the solar system, as well as the forces such as magnetic and electric that make up this region of space. Non-Newtonian physics. We learned from Einstein's special theory of relativity that mass, time, and length are variable, and the speed of light is constant. And from general relativity, we know that the gravitation and acceleration are equivalent, that light bends in the presence of mass, and that an accelerating mass radiates gravitational waves at the speed of light. Spacecraft operate at very high velocities compared to the velocities we are familiar with in transportation here on Earth. Since spacecraft velocities do not approach a significant fraction of the speed of light, Newtonian physics serves well for operating and navigating through the solar system. Once we begin to travel between the stars, velocities may be large enough fractions of light speed that Einsteinian physics will be necessary for determining trajectories. Thanks for watching my segment on the solar system and interstellar exploration.